Okay, so let's start. This is about the abstract interpretation of OCaml programs. This is very much work in progress. So please be tolerant about the current state of the affairs. So this project is developed at INRIA Rennes, and there are several people working on this, Pierre Lermusio, Thomas Genet, Thomas Jensen, and I would like to thank Pierre Lermusio, who really gave a great boost to the project when he joined it. And this is funded by INRIA and Nomadic Labs, who is a company that develops the Tezos blockchain. And all the story really started when I discussed with Nomadic Labs engineers, because they were a bit concerned about their code, because they have a large piece of code that changes quite quickly and that they have to release on a regular basis. And although they're very serious about code reviews and testing, well, they are keen on having greater guarantees about what they release. So especially exceptions, because they can make your program stop really abruptly. So this is a very humble attempt at a recurrent problem in the ML community, which is trying to detect unquote exceptions. So the Salto project is about mainly detecting unquote exceptions, and these can arise in many cases. So a user can provide assertions. You can just forget about handling division by zero, of course, but any access to arrays or strings also checks for bounds, and these can raise exceptions. You also have in OCaml this polymorphic comparison that may raise exceptions when it's recursively calls at some point on functions. Seasoned programmers sometimes use unsafe functions to squeeze more performance, and you would like obviously to also have the guarantee that they are called on arguments that are okay for these functions. The long-term goals of this project is to support as much as OCaml as we can, but that's many features to support. In particular, algebraic effects won't be easy to analyze, I think. I would also like to be able to detect some parts of the OCaml semantics that are explicitly not defined, because it makes the life of the developers of the OCaml compiler easier. And one of them is the order of evaluation. Okay, so as a midterm goal, I would also like to detect whether a program depends or might depend on this order of evaluation. And I'm sorry to disappoint many people in this room, but this is really a way longer term goal to support concurrency and parallelism that was recently introduced in OCaml 5, and also to support the parts of the standard library that rely on how the data are actually represented in memory that is gathered in the OBJ module. Okay, so today I'm going to talk about mainly the first part. So it's a long-standing, this problem has been studied many times in the ML community. If you're not familiar with this, you can split the related work in two big families, type and effect systems on one part. And these are great because they are modular analysis and have fairly good performance, but the precision is not so great, especially when you have to deal with user-provided assertions. So one of the main related works in that area is the work of Leroy and Pesso. And the other half of the related work is mainly extensions of control flow analysis. Okay, so these are whole program analysis that are not modular, slightly more costly, but they have the ability to get more precision, especially when you have to analyze user-provided assertions. And maybe the work that is closest to what we've done so far is the work from Yi from the 90s that also developed a static analyzer, an abstract interpreter for standard ML. Okay. So the principle of this analyzer is, this should be no surprise to most of you, given any sub-expression of a program, call it E, try to find out an overall approximation of the values that it might evaluate to. And also, in case this evaluation might raise an exception, try to find out an overall approximation of the sets of exceptions that might be raised, and also an approximation of in which call stack it might have been raised. Okay, and actually we are going to analyze only expressions that we are sure will not be unreachable. Okay, so that means that presumably only the functions that will be actually called in your program will be analyzed. Okay, if you have a library but never call any function, that's easy. The behavior is just, you just create a bunch of closures, no exception will be raised. Okay, and we base this work on a former work of ours that we published at PLDI a few years ago that was dealing with the abstract interpretation of the pure lambda calculus. Okay, so the main novelty that I'm going to talk in this talk is an abstract domain that represents sets of values that are defined recursively, and also another fact about the implementation, which is the use of what we call a dynamic fixed point solver. Okay, so what we have achieved so far is we have an abstract interpreter that runs. And so we support higher order programs, mutual recursive functions, a fairly large subset of the OCaml language, so algebraic values, deep, but not only shallow, but very deep pattern matching is supported. It's not written there, but gathers are also supported. Of course, we handle exceptions. Modules and functors are supported. That was a big amount of work. But so far, we are not able to analyze programs that perform mutable changes or mutable data structures. We are not able to support laziness objects, and I told you already, OCaml 5 features. Okay, so what is interesting is that the whole analyzer is a big functor that is parameterized over the domain of values that it uses. So it's easy to change this domain and make experiments. And it is a forward analysis, okay? So it means that it's not guided by which assertions are written by the programmer. Okay, for each step of the program, it tries to do its best to find the most precise information it gets. It is context and flow sensitive, and contrarily to F lambda 2, we are not trying to infer any relational information so far, just because we haven't found enough time to do it yet. Okay, and I propose to have a quick demo. How does it work? Is it big enough? Okay. So here I have written down, have copied the type of the list that you all know, of course. This is not important and should be removed. Up. And I have rewritten the for all function that tests whether a property holds for every element of a list. Also have written down the filter function that only keeps elements of a list that satisfy some property. Okay, and I basically built a list that may contain some integers. Then I filter out the results so that I keep only these elements that are above 17. And then I write this assertion that, well, the list should only hold integers that are above 17. So the analyzer should tell me that no assertion is raised, right? So here I have the analysis results. You can see that, yeah, apparently no exception was detected. And I'm not lying to you, because here if I assert instead that every element of the list should be strictly above 17, and then if I analyze again, then this time I will get the fact that, well, assert failure might be raised, okay? So that's an easy example. I have maybe another one that is more interesting. It's a bit longer, and the analysis takes 30 seconds or so, so let me start it right away. And so it's basically a copy of a part of the map functor that you have in the standard library. That's interesting code, because you see there's a lot of exceptions that might be raised. It depends on internal invariance of this data structure. And what is even also interesting is the fact that the user code that calls, let's say, the merge function, so it provides a function as argument that has this interesting case where we basically all write this down when you use the merge function, that if the function is given the non values, then this code should never be called on that case. So you see I could have written assert false, but I have written raise impossible instead. And I hope that, well, the analyzer will tell me that indeed impossible is never raised. And let's have a look. Yes, it has finished. Let's have a look. So what are the alerts? Okay, so invalid arguments might have been called. If you look at the results, please trust me, it's only the rebalancing function that raises this invalid argument exception. And if you look at the rest of the code, what do we have? Do we have any other alarm? Yes, okay, we have one internal assertions that it was not able to prove could not happen, okay, but what is really important from my side is that this raise impossible is shown to never happen, okay? And that's not easy to obtain as a result. So how does it work? So we basically have this, so this is a simplified version of the domain of that represents the sets of values. Okay, so it has different cases. Okay, so it's a big recurse that says it's either these possible values that are integers that are represented by an abstract domain of integers that you can choose, or it's a bunch of variants. So these constructors given to arguments represented by the same domain, or pairs of the same things, or these possible functions with this closure environment or top. Okay, but if you have only this, you cannot represent interesting information about, say, lists, because you only have you can only represent a list of size up to some depth. Okay, so here basically I added I added a variable and a constructor that says that, well, this is a recursive definition. So basically, if you're familiar with equirecursive types, this is the same idea. The thing is, this operator new, by default, is never there, but it is introduced by the widening operator, which is an operator that is essential in abstract interpretation that somehow generalizes the results so that you get so that you find some fixed points. Okay, so all the cleverness of the abstract domain relies in this widening operator. And I won't have time to tell you about. So of course you can represent using this the piano numbers, but you can also represent a set of closures that are the continuations that would be passed to a CPS version of the factorial function. Okay, so the continuation of the CPS version of factorial is the continuation may be either the identity function, it is the final call of the CPS, or it's going to be take the result, multiply it by n, which must be an integer greater than 1, and then pass it to the continuation, where this continuation is again, the same thing. Okay, so this is the kind of abstract values that the analyzer is able to infer automatically. So, as I told you already, the main ID should be familiar to you if you know equirecursive types and union types, because these sets of values can represent sets of values that are not well-typed. Okay, so I can say it's either an integer or a pair of values, for instance. But the ID it was already present in the 90s when Hentenrich and Le Charlier analyzed product programs. Okay, and if you are familiar with tree grammars or tree automata, well, you can see this also as a subset of these well-known devices to represent sets of trees. And what is interesting is that so you can see these abstract values in two ways, either as graphs, so taking the tree automata point of view, and for them you have efficient algorithm to compute different operations on them that are necessary to define an abstract interpreter. Or you can view them as terms with bound variables. The alphas are these bound variables. And if you represent them as terms, well, you have the ability to perform hash counting and memorization. And that was not done by Le Charlier before. But this is essential to obtain decent performance. When I implemented it, hash counting and memorization, I obtained a 10x improvement. And this is not something surprising. If you read the papers about abstract interpretation for C, like the Astray papers, they have the same, they notice the same improvements when they use hash counting and memorization. Okay, so if we try to compare this to the work of Pessoa and Leroy, well, they also infer recursive types. But their technique is based on unification, whereas we instead use a fixed point iteration, so that's a different technique. They support arrow types, okay, it's a sort of traditional type and effect system, so they have row variables to have polymorphism on effects for arrows. We do not have arrow types, but we are able to infer sets of closures, which means that when functions are really used as first-class citizens in a program, we might be more precise than Pessoa and Leroy. Considering integers, Leroy and Pessoa were able to express that, well, this value should be an integer that is either 1 or 3. Okay, so a finite number of possible integers, or any integer, or, well, some integer represented by some row variable row that will be instantiated later. Okay, but here this is quite limiting information, and we don't make a choice in our implementation about how to represent integers. We just provide a bunch of abstract domains, classic abstract domains to represent integers, and it's up to the user of the analyzer to make his choice. When we compare the control flow analysis, so traditionally, control flow analysis in the abstract domains, they try to avoid recursion at all costs, because it's really difficult to deal with. Okay, I haven't told you that the especially the widening operator that introduces the mu construct, well, it's difficult to get it right. Okay, so in all the previous work, they avoid this recursion, and instead they encode the recursion to express recursive sets of values using pointer indirections. But these pointers are abstract pointers in an abstract heap. Okay, so here it's basically the same value that I've showed you before. That is the set of continuations that are passed to the CPS factorial function. But here you notice that the recursion here goes through a pointer that is defined in an abstract heap. Okay, so and in modern papers about CFA, this is explained the following way. Well, it basically mimics the way a compiler works, because it will allocate these functions in the heap. But in practice, it inhibits quite a lot of sharing between abstract values, because what matters most is the names of these pointers. Okay, and this is also the main ingredient that makes these analyses converge to a fixed point. It's that the possible names of these pointers are in a finite number. And another thing that is not that great about the previous work about CFAs is that this abstract heap that is used to represent these indirections is global and used in a context insensitive way, and that hinders them from refining information when traversing a if-then-else branch, for instance, because to keep the analysis correct, well, you can't do that always. You basically have to perform a weak update instead of a strong update, and you lose a lot of information. So I told you that we define the analyzer using a dynamic fixed point solver. You might not know what this is. So in a nutshell, it's a function that has this type. It takes a functional as argument and returns you a function that is supposed to be a post-fixpoint of the argument. And it allows you to define quite easily and elegantly an analyzer, let's say here for the lambda calculus. So I apply the fix operator to a functional that expects as a first argument analyze, which is the fixed point that we are expecting. And that takes then as argument two things, a pair of a term f and the environment, and that will return as output the abstract values. And basically, it looks like a standard interpreter almost. So in the variable case, I just look up in the environment. In the lambda case, I will just create a closure. Here it's an abstract closure, okay? And in the application case, well, I will analyze the two parts, T1 and T2, and then I will ask for the closures in V1. And for all these closures, I will, so a closure is a variable, a term, and an abstract environment. I will call the analyzer on this term on the environment that is extended with the value V2, which was obtained by analyzing T2. And once I have computed all these possible results, then I take the join of them. So obviously, it means that the cleverness of the analysis doesn't rely on this part. It's really easy. So what is really subtle is fix, the function fix that implements the iteration strategy, and of course, the domain D. Okay? And well, so we implemented the analyzer using this style, and we're quite happy about it. So again, this is not a new idea at all. The same guys, Hentenrich and Le Charlier, used the same technique to analyze product programs. And then the same technique was again advertised by Dare and his co-authors on this beautiful paper, Abstracting Definitional Interpreters. So they advocate the fact that you should define your abstract interpreter in open recursion style. So it's exactly what I told you on the previous slide. And it's actually used for, I would say, real analyzers. There's an analyzer for C programs that detects data arrays that is called Goblin. And they are extremely happy about it, obviously. But if you have paid attention on this week on Tuesday, there was also work talking about this, the fixed point algorithms session. Okay, so it's an idea that is very much in the air these days. Few information about the state of the implementation. Okay, so on the top is the very beginning of the compilation pipeline of the OCaml compiler. What we take as input is not is an AST that is obtained very early in the compilation pipeline. It's the types AST, and essentially it's an AST that has many cases. It's large, and we desugar it to a form that is a bit more simpler and easier to manage in our analyzer. So what is nice about the AST is that the names of the variables are resolved. You have access to all the type information that you need. But what is not great is that you have some redundant parts. So you have many parts that actually perform some pattern matching. You have several constructs that perform exception management, and the order of evaluation is not yet made explicit. Okay, so we have a first phase of desugaring that essentially introduces exactly one construct for pattern matching and exactly one construct for exception handling. Here it's basically a construct that expects two continuations, the success continuation and the exception continuation. And when possible, we introduce let bindings just to make the order of evaluation explicit. And another thing that is very important for us is what I call pattern disambiguation. So basically here, you all know that in ML and OCaml, when you evaluate some pattern matching branches, you evaluate them in the order that was written. So when you know that some branch has failed, you get some more information. So what we do is that we make this information explicit. So here we know that on the second branch, well, this underscore cannot be sum of something. So this is what we call complements, and there are several papers that talk about this already. And yeah, so this information is also very important, not just for our analyzer, but for any analyzer. If you guys want to analyze the OCaml programs one day, well, you will have this information available if you start from the Salto AST. Maybe it's time to stop. So this is very much a work in progress. So far, we cannot handle the whole programming language, the whole OCaml programming language, but still our abstract interpreter is able to detect unquote exceptions fairly precisely. What I've showed you is a new abstract domain that represents inductively defined sets of values, and how you can use a dynamic fixed point solver to define your own analyzer. And I'd be happy to catch any questions that you may raise.
Thanks. So first, there are two parts of the question. The first part is how much do How much precision do you lose when you have something you don't handle, a construct you haven't modeled yet, typically mutability? And second part, how do you intend to deal with mutability?
Okay, so the answer to the first part is really easy. So far, we fail. Okay. But of course, yes, we want to handle mutability. It's in the pipeline. Yes.
Thank you for the fun talk. So you've chosen to build this abstract interpretation on a quite early intermediate representation. You could imagine choosing a later one. For example, we just saw a great talk about f-lambda2. And I was wondering about the trade-offs of those choices. I could imagine that a later representation might be simpler to work with because everything's already been destructured into blocks and you don't need as many different types in your abstract domain.
Yeah, so it's true that if you go later in the compilation phase, then your AST will be much smaller. That's true, but you also lose all or most of the type information. So far we don't use the type information, but we really want to, because sometimes the widening operator just makes the wrong choices, and in these cases it would be great that the output is refined by the compiler already knows. What else? It's also, I think, but please correct me, Pierre. I think it's also a bit easier to get more precise program locations so that you can more easily report to the programmer.
Any other questions?
So I'm wondering, how do you do the hash consing on the recursive types?
Well, these are just trees. Okay, so you have a node for the mu, and then the way we represent bound variables is using Dearborn indices. So you have a normal representation. So then you have just trees, and it's easy to hash count them.
It obviously you implemented enough so you can try on larger programs. So what's your experience? What kind of large program you tried and how well it?
So far we have not tried on very large programs. Okay, the largest program we have tried with is maybe 200 lines. So we are very, very far from dealing with real-size code. And of course, there's this question of scalability. Will it scale to a large code base? So definitely not to Jane Street's code base. It's way too large. But I can't answer this question yet. My hope is that it will be okay. But I know that some trade-off will have to be made to degrade the precision in some cases, or maybe to find a more hybrid approach between whole program and fully modular function by function. Okay.
But scalability is, it just fails because out of memory or other things, so it just takes too long a time, then you just give up. And what's the?
No, it's the time.
What's the time? Okay.
Yeah. Memory is okay-ish. Yeah.
Okay. Any other questions? Well, let's thanks, speaker again.